Recording in progress.
Alright, good afternoon everyone, and I've been waiting for this time from yesterday. But anyhow, it's a good time to start, hopefully, because I think we had a lunch, and I hope you are not feeling sleepy right now. I'm Syamantak, as all of you know by now, and I work on mainly Alright, so I mainly work on looking at the vascular system, looking at more on endothelial cells and how they behave and how they interact with different cells. Primarily, the lab is working on developing models for atherosclerosis. Alright, so before I start, I just again, first of all, I forgot to thank the organizer, Prof. Syamantak and Prof. From ENS, and of course hosting here the ability case in Paris. And then as I was speaking about, we come from Prof. Syamantak, Prof. Rajdev and myself, we come from Pilani. The campus is beautiful. It's like oasis within the middle of nowhere. I think people who have visited here must be knowing that it is within the in Rajasthan state of India. And this is the iconic tower, the clock tower we call them. Right, we call it the clock tower. And this the building you see over here is nothing but it's called as a new academic building, constructed back in 2012, 13, I suppose. The beauty about this building is that if you see this building, it goes down, and on the top you have a garden. Alright. Now, why there is a garden? The fact is that in Pilani you have an extreme weather. Now, when you talk about summer, it will be like 50s and 50 plus, and winter it could be even -1 sometime. Now, when you take a classes in the summer days of April or May, you can imagine what will be our situation. Of course, there is air conditioning, but you have to make the process to be efficient, right? And that garden over there on the top of those, so these are all classrooms essentially. So this actually kind of give you that week of controlling the temperature better, and you have a pleasant experience when you go to the class and take the classes. And we call this plan is magic, and of course the students also say the same thing. You are all welcome. If you are not there, I think it will be a better experience. I know the extreme weather, but of course there are times when you still have beautiful weather over there. Alright, so before moving on and talking about today's talk or the work that I'll be presenting to you, this is some of the papers that we have actually published in last few years. I joined in 2017, and then we started working on, then getting grants and all those things happened. But primarily the lab works in 3 different modules. One is to look at how the hemodynamic forces because we work in vascular cells, and we look at how hemodynamic forces reshape the architecture of the cell on the context of biochemical as well as the shape of the cells, and that lead to diseases like atherosclerosis, right? Lab works on epigenetic processes, the process that goes beyond the gene and defines how the gene is going to be expressed in our body. So we work on that. We also work on that if you are too sweet, how that can really affect you. So if you are too sweet, that will be a problem for you. It's not that. How much sugar you have in your blood, and that sugar can actually kill you because it reprograms the cell and can cause changes in your genes and can cause diseases. We also work on fundamentally trying to understand how the epigenetic pathways are actually driven by changes by post-translational modification of the protein, and we published recently a paper in Nature Communication where it showed that post-translational modification of one of the epigenetic modifiers controls its fate by deciding its stability and its catalytic activity. So today I will be focusing on the part where we published a couple of papers. One paper is actually in revision in JBC, And the content of my work will be on today's presentation will be introducing you to the endothelial cells and cardiovascular disease and atherosclerosis. And they talk about how these hemodynamic forces reshape the endothelial cells and that prime them to have the onset of atherosclerosis signaling and that lead to the disease progression. And finally, I will be showing you some preliminary data that we have generated where we've seen that how these endothelial cells in the context of the flow reshape cancer cells to kind of attach to the endothelial layer and then kind of reprogram them to cause a colonization of those endothelial cells or the cancer cells. Now it is important to know that we are talking about tumors and cancer, but in the fact is, if you look at the mortality rate and the number of people actually die every year, cardiovascular disease remains the leading cause of death worldwide. Okay, and you see that this number what I saw here, it's back in 2019. It's almost 18.56 million people have lost their life because of the cardiovascular diseases, and that is not including the patients who are actually suffering from the disease, which could be much larger than that number. All right, and this is going to increase, and this remains to be the leading cause of death for the last 30 years. And what has been found is that endothelial dysfunction is the early onset of the disease that initiate that it will cause changes in the blood vessels that captures those inflammatory cells and eventually cause the onset of the atherosclerosis process. All right. So now let's look, because many of you are from engineering background. Let's try to look at. By now you know about CTCs, you know about cancer. Let me tell you about what is endothelial cells. Now, endothelial cells are nothing but it is the cell that makes your blood vessel. That's a primary cell that faces the blood and eventually that causes the changes within the, that basically controls how these cells within the vascular structure will be behaving. Okay? And that is so your endothelial cells are the innermost lining of the blood vessels. Now, why it is endothelial cells are important? Endothelial cells are very important to maintain the homeostasis of the blood vessels. Imagine that when we talk about contraction and relaxation, your blood pressure, these are all being driven by the fact of how endothelial cells produces certain factors like nitric oxide, a gaseous molecule that affect the smooth muscle, right? So if you are hypertensive, you can blame your endothelial cells somewhere because maybe your endothelial cells are not producing enough quantity of nitric oxide to control your blood pressure. All right. So endothelial cells plays a major role in multiple homeostatic pathways. So we talk about inflammation. We talk about platelet activation, maintaining the blood pressure, maintaining a good cardiovascular health. These are all driven by the health of your endothelial cells. So you need to make sure you nourish your endothelial cells, you make them in a proper state to have a good cardiovascular function. And what happens if there is a dysfunction of these cells? You have multiple different diseases. That includes atherosclerosis, different peripheral arterial diseases, and metabolic syndrome, obesities, and chronic kidney disease. These are all which is the consequence of the endothelial dysfunction. Now, let's come to the point where I say that why biomechanics? Why the mechanical changes are very important in the context of how endothelial cell behaves. Now, what we've shown that if you look at the onset and progression of atherosclerosis and where exactly the plaques are developed in humans, it majorly happens in the areas of palpitations or areas of curvature, suggesting that the hemodynamic forces that is imparted by the blood flow is something very important to maintain a good endothelial behavior. All right, and that suggests that the hemodynamic forces or the wall shear stress that being imparted by these hemodynamic forces of blood flow is something that maintains the endothelial behavior. So as you see here, you see this is aorta taken from a mice which has been fed with high-fat diet, and as you see that this aorta in the bifurcation area, you have a development of the plaques. And this is consistent even in the humans also, right? And that suggests that these hemodynamic forces somehow kind of control or predispose the endothelial cells. If you have an alteration in these hemodynamic forces, this predispose endothelial cells to recruit all these inflammatory cells and eventually cause the formation of the plaques or atherosclerotic plaques. All right. And this has been already proven. There are a lot of papers, so I don't have to focus on those. And it's been shown clearly that atherosclerosis is being driven by endothelial dysfunction that can be controlled by the hemodynamic forces, especially at the bifurcation or in the curvatures. So how does this atherosclerosis develop? It's all about initial phase of triggering of the endothelial cell, attracting inflammatory cells, assimilating those inflammatory cells, and these inflammatory cells include like monocyte macrophages, and that eventually attracts all those cholesterol, the high fats that we have into your renal circulation, and that being attracted by those monocytes to form a cell called as a fold cell. So macrophages eventually differentiate to form a fold cell, which kind of deposit all those fats into the blood vessels, and therefore cause the formation of the plaques. That eventually creates more complex situation. You can imagine that, your platelets are how it gets activated. It simply gets activated if they are kind of going to hit something that, suppose we have a cut that hits, platelets hits those physical, cut, and then therefore it gets activated. So eventually what you see, you have foam cell formation, that lead to the activation of the platelets. So you have now a thrombus formation, and it creates a huge complexity, eventually leading to calcium deposition. So you have a calcified plaques, which are also going to be more detrimental, and they are kind of hardened plaques which are very hard to be removed. All right. Now, because I said that these hemodynamic forces drives this function of the cells, that means the initial phase of recruitment of the inflammatory cells are driven by the changes in endothelial markers, kind of additional molecule that attracts those cells. So it is very important to study how these hemodynamic forces drives them. So the fundamental question that I asked when I was, I joined with Pilani, and the first question I asked is that how do you really mimic this condition? Because majority of the models that have been developed so far, they are parallel plate models. They are models that are not mimicking the exact, the blood vessels into our system. Secondly, the question we ask is about what is the, how does changes in the bifurcation angle kind of predispose the cell to have more inflammatory state, and they will be preferred to develop the plaques than the other ones. All right. So biologically, if you look at in your system, you have blood vessels which are ranging from 20 degrees angle to an angle of almost 100 degrees. Right. Is there any preferences for developing of the plaques because of the hemodynamic changes? Because we know as engineer, you will appreciate that as you change the bifurcation angle, there will be a different kind of hemodynamic forces being generated within these blood vessels. All right. So we asked this question, and it was back in 2017 when I went to, I met this gentleman who's also a colleague from chemical engineering department. That's a good thing about being in engineering institution. You do science and you interact with these people. So I met him in one of the workshops called as the intensive teaching workshop, ITW. And Razik was one of the resource person during that time. Resource person means who is expert. He's a great teacher. If you listen to him during the classes, he's an amazing teacher. So during the tea, I was talking with this gentleman from chemical engineering because we are together in the ITW. And we found that we have some common interest. And what is the common interest was that he is a person who does CFDs, computational fluid dynamics. And I'm a person who works on blood vessels, right? Pure math. But the time he started speaking about his part, he was talking about some mass movement, equations, and I do not understand that language at all. Come on, I do not understand. Then I said, you are smart, I do this too smart also, right? I started speaking about blood vessels, the intima, media, he was like, surprised, So we thought we need to have a common partner, and that common partner came to a beautiful combination because in which Pilani we offer a dual degree program, right? Where the student also have a science degree as well as a dual degree in engineering. And we found a perfect match who is also having interest, and this the student called Mr. Ishan, he was a mechanical engineer and he also had biological sciences. So we found a common match. We found, we have an interpreter who can interpret both the languages, and let me kind of put together and see how it can be worked on. And he's a very smart guy, and we also put one of our PhD students and who worked eventually along with Ishan on this problem. Now what we did, is that we try to look at how can we model the system and try to develop something that actually mimics the blood vessels. And we went on to and looked into the website, and we found that there is a kind of website that you can look into, which is called as a Syamantak. And Syamantak has lot of CT scan images of human heart, and they have a lot of coronary arteries images. So what Ishan have done, Ishan actually took those those images and tried to kind of design something called as a computer-aided design file for one of those artery from the right coronary artery of human heart. All right, and we did that. That has a natural bifurcation of around 52-degree angle. Right. So we took one of that, as you can see here, and he has designed a CAD file. And after designing the CAD files, we went on to doing a 3D printing. That's a simple 3D printing. It's not a bioprinter, but we did a simple 3D printing of that. And then we casted them into a PDMS mold. All right. So we casted them in PDMS mold, and now what we have finally, we have this the cast which we can use to grow the cell within the channel, and this channel will be actually coming from a human right coronary artery. All right. And now we can apply the flow of media. If it grows cells flow of media, you can define what is the rate of the the flow, and therefore you can also control the range of the wall shear stress pattern within these particular channels. Moreover, what we did, we also created different angles. So what we did is we created angles. So we had, as I said, this is naturally it was a 52-degree angle. So we took the 52-degree angle. We remained one to be in a constant, so we didn't change. One remained to be static, and we moved the other one and changed the angle accordingly from a range of 30 to 80-degree angle, and see what exactly the phenotype of these cells or endothelial cells that are grown into glucose. We also did a lot of analysis, and we found interesting observation we had. We found that the wall shear stress pattern drastically reduces on these variable regions where actually the arm which have been changed. You see there is a drastic reduction in the wall shear stress pattern on those particular walls. So we wanted to see if this is also kind of shows the effect on the cellular level. So we use two markers which are endothelial functional marker. One is a good guy, that means it supports endothelial cells, and another one is the bad guy, which means when it expresses, it's an addition molecule, it recruits the monocyte to have information. All right, and we looked at that, and we found we did some tile scan imaging, because you can imagine that this is it's not a microscope, it's not macro, right? It's a bigger size, almost 2 to 3 millimeters. So we have to go for a tile scan. We're scanning at one part at a time, and we did something like 6 hours scanning for only one image. All right, and what we found here is that the 60-degree angle somehow showed the reduction in the good marker and increase in the bad marker, the one that recruits the monocyte and cause inflammation. All right, and then we analyzed those data, and we found that in fact the 60-degree angle shows the minimum level of eNOS, the good gene, and maximum level of the ICAM1, what was the additional molecule of the bad gene. So that means it basically exactly matches with the data that we have got from our fluid dynamics analysis. We also did some more analysis, because as I said, we made one to be variable and one to be fixed. Interestingly, what we found, if you look at the variable arm, the output velocity also reduces. In fact, the wall shear stress is minimum in the one which has the variable arm, okay, not the one that is static in nature. Fine. So we majorly look at those arms. In fact, we have also done the comparison between these in the expression of these markers, but we majorly focused on the arm which shows the minimum wall shear stress pattern. And we'll then look onto all these markers in a more focused way, looking at the areas where we have the D-flow and the steady flow. So this steady flow is the flow which we find that in the location beyond this, you have a steady flow. We have also the vessel over there, and we mainly look at D-flow in these areas, in the D variable and D fixed. And then we found that yes, in 30-degree angle, you don't see any changes between the D fixed and D variable. The eNOS, the good gene, remains to be constant. You also see that there is no much increase in the expression of the ICAM1. And then in 60-degree angle, you see a complete difference. You see that both d fixed and d variable shows a drastic difference into the level of ENOS level, while they have also increased in the gap change, which is the ITM1 expression. That means they are more primed to recruit the different informative cells, including the monocytes. Alright, and then we went on to 80-degree angle, and we found that the changes there are changes, but it is not as robust as you see in the case of 60-degree angle. And then we looked at the more of the physical property of the cell, and we did some scanning electron microscopy images. We did some CD144 staining, which is the cell-cell junctional marker, and we also did the attracting staining. And what we found is that there are a lot of changes in the shape of the cell in the context of if you look at typically the endothelial cells are elongated. It's like a cobblestone structure, and as you expose them to these different variable of the the D flow or the bifurcation angle, you see the cell shape completely altered, and you see that it's completely like a circular cell in the case of 60-degree angle, right? And suggesting that these cells are kind of deformed in this particular flow conditions. Then we did a monocyte addition assay. What we did is that we label the monocyte cells with dye. That means all those red dots that you see are essentially our monocyte cell labeled with red dye. And then we ran it into the flow system and with different angles. And what we found is that in the 60-degree angle have the highest number of monocyte cells that attaches to those area of the beam flow. Okay, so that actually matches with the concept of loss of ENOS, gain of ITM1, which is the addition molecule, and increase in the number of cells monocyte that get recruited in those areas. All right. So finally, to summarize this, we have summarizes that this bifurcation angle dictates the endothelial response, like changes in the wall shear stress, and anything beyond, somewhere between the 50 to 60-degree angle, they are more predisposed to create a few kind of hemodynamic forces that makes the endothelial cells to be, more inflammatory and recruitment of the, the inflammatory cells, right? And this we have published in Conjugation Biology in a couple of years back. And the relevance of this study is that the findings being made in atherosclerosis with prediction from patient-specific, angiograms and guides surgical planning for coronary intervention. In fact, we have also found a couple of studies that also prove that if you look at the location of the development of the plaques in humans, majority of them in fact takes place within an angle of 50 to 60 degree, bifurcation angle. So that exactly supports our data, and this was something we have published previously. Now I'll change the gear a little bit because this conference is all about cancer cell and how it's interacting with different cells. So we'll talk about. I'll have only 2 more slides where I'll show you that how this flow can dictate the endothelial changes in the kind of expression of the addition molecule, the preferred polarization of the cancer cell. Right? So what you know that the cancer cell or the CTCs are someone that will not move alone. I think Rasid has already spoke about that CTCs are something that will not go alone, but they will come together and form or capture those platelets to cover them up to protect them from the fluid forces or the hemodynamic forces and protect from other mechanisms. So these cells are somewhat roaming around within the blood vessels with the help of other supporting cells like platelets, and then that cells eventually colonizes in certain areas. For instance, in the lung, because we know in majority of the cases metastasis happens in the lungs. So that means they have a selective preferences on which bed they will bind, and this binding of those CTCs to the endothelial layer could be defined by the fact of what kind of additional molecule do they express, the endothelial cell express. But do you know that so we know that, of course, tumors causes a change in endothelial cells, because remember one thing, that when a tumor has to grow, it essentially has to make sure that the blood vessel formation takes place, right? So it secretes a lot of growth factors to promote angiogenesis, which is called as a tumor angiogenesis, all right? Now, in this case, we were more interested about whether these group of circulating tumor cells, when they are present with the platelets, can it revamp the expression of the addition molecule within the endothelial cells that can attach them to the endothelial layer and therefore can cause a more preferred landscape within these endothelial cells to cause colonization, attachment and colonization of the tumor cells. So with help of last week's lab and two of our PhD students worked together, and in fact we have also got a grant from the Department of Biotechnology together. And what we showed here is that if you look at the endothelial cells, so what we have done, we have basically taken the flow model, and this is more of a laminar flow, not through the bifurcation angle. We did not look at that context, but we have kind of created, we have mixed the cancer cell with the non-activated platelets and activated platelets and run through those endothelial cells, layered endothelial cells within the flow condition. And what we found that these endothelial cells which are exposed to this condition have expression of integrins beta 3 and integrin beta 1. They have an enhanced expression of these two markers, and they have a reduction in expression of markers like p-selectin and ICAM1. Okay? This gives a very interesting phenotype. What is the interesting phenotype? If you look at the p-selectin and ICAM1, they're more of an inflammatory phenotype, right? And you know that the p-selectin and ICAM1's expressing endothelial cells are predisposed to apoptosis, right? So what the cancer cell knows, I need a bed where I can bind myself, but I don't want it to kill. There shouldn't be dying because I have to colonize and I need the help of the endothelial cells. So it creates a situation where you see a reduction in the level of the inflammatory addition molecules, but you see an increase in the integrins that possibly help in the attachment of those cells to the endothelial layer, right? And that's, we believe that this integrin beta 3 and integrin beta 1 are the one that possibly helps in the attachment of these cancer cells or CTCs to the endothelial layer. In fact, we also see that there is an increase in the expression.
But in that case, you don't need the activated or non-activated platelets.
Yes, it doesn't matter about activated or non-activated, and we are expecting that maybe these cancer cells are actually in fact bound to a non-activated form of the platelets, but we do not know how it exactly happens in the in vivo condition. And we also see there is increase in VEGF-A, which is a pro-angiogenic marker, so it also induces expression of VEGF-A. And we also see expression of S1. S1 is nothing but a downstream target of the notch. So that means it somehow reprograms the endothelial cells, changes the landscape of its addition molecule, and possibly prefers a situation where it is kind of inducing its attachment and colonization in certain areas. But these are very preliminary data that we have. So with that being said, I will finish my talk. I hope I'm right on time, much early on time, right? So the acknowledgement, I must thank all my PhD students, especially this work has been done by Yash. Yash has just completed, he submitted his thesis and defended it, and all other PhD students, my collaborators, including Professor Rasdeep, we are working now in London also, and all the funders who has funded this project. And of course, CEFIPRA and Department of Science and Technology for all the support given for this particular workshop. All right, I'll be happy to take any questions.
Have you looked at the ZO1 endothelial junction proteins?
No, we have not looked at ZO1, but I think because we did not focus on we are yet to be kind of more going in details of cancer cell and attachment to this.
No, even for you, I'm talking about your
No, we did not do that. Because we see a lot of changes in the expression, because we know that endothelial cell also goes through something called as endo-empty, endothelial to mesenchyme, and the expression of these markers also changes, but we have not looked into that topics.
And the second thing is that kind of I am giving that your question that you asked. Are you considering the softness of the channel?
No, we are not. We did not look into the softness of the channel.
But are you planning to do that?
No, so what we have done, when we created the PDMS, we have moved this channel to gelatin. Because our primary endothelial cells will not grow either in PDMS or in glass or plastic. So we coat them with gelatin and then eventually grow the cells. That gives some softness, but I will not say exactly the mimics the in vivo conditions.
I'll talk to you.
Yeah, sure.
OSI, oscillatory shear index is important. It's a
Very important. Very important.
Corinna has done a lot of work on this.
Yes, in fact, we have not. That is one of the points, because the pump that we have used that doesn't create oscillation, and oscillation is an important point that needs to be remembered. So this is a simple peristaltic pump. It's kind of creating a flow, a stock flow, right? And the oscillation is one of the important parts that we missed out. Even though in our CFD analysis, and we did this because see, when you're doing a computational analysis, it's easy to do, but the pump was something that we do not have and we need to do.
So this is
Yeah, you need to take a photo of that.
He's my son and he's going to ask me a question. I'm sure that he was going to ask me. Yeah.
the,
And the
the
question is the planted.
like this is probably the first time I'm seeing my dad giving a presentation in front of me. So my question is like you mentioned about platelets shielding the cancer cells basically, and they are interacting in the endothelial cells and all that. My question is that like applying basic like common sense and logic that I understand. If there are three friends and there are three people, the first person does not know the third person, but the second person helps the first person, is like supporting the first person. The third person automatically believes, okay, the first person must be friend. So in the sense over here, doesn't the platelets shielding the cancer cells inevitably like reduce the immune response? Like they change the antigenic profile, I would say, of the cancer cells, which limits the immune response. That's
I
my.
need to tell your mom that you asked me the question. I know, but it's a good question. Yeah, means think about it. Like a tumor cell is a cell that pulls all other cells, including our immune cells. Right?
Okay.
So it's going to take all the help it can take from all the supporting cells, just by pulling them, right? And I think what is happening is that it's all about kind of pulling the platelets, saying that here you help me, and possibly in part it may have some kind of consensus relationship eventually, right?
Okay.
So that we do not know. It is pulling the platelets and attracting them to form that shield. That is
Okay.
not
Actually, answering to this, they express markers that allows the platelets to bind. And this is specifically done so that blood-borne immune cells cannot recognize the tumor cells.
Oh.
And also this reduces down on the shear stress that the cells experience.
Oh,
because
right. These
because
platelets
the
are taken
shear
care of.
stress is now being experienced as a first effect is coming up on the
Platelets.
platelets and not the cells.
Wow. Yes.
Thank you.
Thank you.